welcome back. So it's time for the second talk of today's session, and it's a pleasure to introduce Arnaud Brodier talking about moduli spaces and the tensor product for representations of the Cuntz algebra. Thank you.
All right, thank you very much. And thank you for the organizer. It's such a pleasure to be here at this moment. We see all these friendly faces and see this beautiful city. So thank you so much for organizing it and for inviting me. I'm very glad to be here. So my topic will be about operator algebras and also other things like natural algebra, like just straight algebra and also groups. And I'm going to talk about an efficient way to build some representation for various objects and various objects in mathematics. And really, it came from an accident in mathematics. And it came from the desire of constructing certain conformal field theory. So perhaps today, since many talks we saw before today were about conformal field theory, I want to show that you never know where you will land. Okay, so I'm going to show that the arrow went very far away from the target for this story. Okay, but nevertheless, this can really give you great output. So let's see that. So all that I'm going to talk about, the initial work was done with Von Jones about 6 years ago, I would say. That really gave like the all the hope and he gave really like the vision where things could go. And then all the technical matter has been done thanks to a very, very gifted student that I met in Sydney, Dilshan. It started when I asked he was just an honor student. I asked him one basic question and he replied to it. Then he said something completely wrong. And then I asked him something hard that I was like, I mean, if one say it was hard, it would be hard for him, but at least he can think of it. And 2 weeks later, he said, yeah, it works actually. I was like, oh, okay. Maybe now we'll listen to what you say a bit more carefully. And indeed, Dilshan did very, very well. And thanks to him, we have now a very nice construction. I will try to show briefly. Okay, so what is the origin of all that? Yeah. So the origin came from this famous question that if you've been in surfactor theory or in conformalnet, you may have heard about, is that when you consider surfactors, so inclusion of, let's say, type 2 factor with finite index, you can look, let's say, at the bimodule category generated by the big one with respect to the small algebra, and you get like a unitary fusion category or a rigid C-star tensor category if you have more than finitely many simple objects. But the point is that you get any unitary fusion category in that way. And you get things that looks like rep of a compact group. You also get things that looks like the representation category of compact quantum groups, and you get even more. So you get like very exotic symmetries. And so, as you know, in conformalnet, in conformal field theory, quantum field theory, you have like very beautiful symmetries that go beyond the usual symmetries given by a group. And that's, you could say, oh, well, okay, the matter at a quantistical scale have much more subtle symmetries. But can we actually have these very, very exotic symmetries that happens in subfactors? And so it's really like a philosophical question, like any of these very weird symmetry, like very rich, I should say, and exotic symmetries of subfactors can be realized by quantum systems. All right, so that was the big idea. And when I say quantum systems, I really think about chiral conformal field theory, like Doplischer, Kastler. And so many people look at these questions like they've been like some specific example reconstruction of conformalnet. I mean, I guess like just today we were talking about that with Terry about the high groups of factors. Like David also have been so much. Fang did like very specific reconstruction and a very meaningful one for very, very complicated systems. Many people in the room look at that. So really the origin comes from those every subfactor and then has something to do with the CFT, let's say. Okay, and that's a question of Von Jones. That's one of the biggest open questions of the field. Yeah, that is still an answer, but every year there are some progresses. Okay, and so what kind of Ron had many attempts to try to answer this question, and the idea was I want to take a subfactor. I'm not allowed to know exactly what it is. It's like a subfactors, and I want to have a nice black box. Maybe not too black, but something you can see something, but give you something, an output, and I want to have a net. Conformal net, and if I look at the representation theory of this one, or maybe I can take quantum double, I get the representation theory of my subfactor. And so one attempt was done with planar algebras. And the whole idea was, if I take one element, if my planar algebra that looks like that, I can do like an action of a group. I will call it T on the circle. Okay. So 2 years ago, I saw a video of Jean-Pierre Serre that was very annoyed that topologists put the index on top. So I know everybody put on top, but since I'm French, I have to follow Jean-Pierre Serre. So now I will put. All right. So if I take one element like that in my subfactors and in my planar algebra that satisfy an isometric condition, it looks like that. I'm able to construct an action on a group on a circle, and from that I kind of get like a baby CFT. It means that instead of having a diffeomorphism covariance, I will have covariance for this group. And this group looks like not much actually. So T, what can do T? Well, locally can scale by a ratio like a 1/2 power n, and it can rotate, let's say, by maybe 1/2 power n also. That's what it does, yeah, locally. And then actually it's something that is piecewise affine. So like abruptly you scale by 1/2 power 1/8 and then 1/16 or something like that. And so you get a model like that. You try to push it by continuity to get maybe rotation groups, things like that. But very quickly, discontinuity arises, and CFT was out of reach. But then you look at what kind of group is that, yeah. And then he was in Vanderbilt at the time. Next door was Max Sapir, one of the best experts on the Richard Thompson's group. And then, yeah, quickly he realized that this is the Richard Thompson's group. Yes, I'm just going to write just a name. And you may have never heard about it. But if you do geometric group theory or infinite discrete group theory, you will probably know it, yeah. So the Richard Thompson's group is one of the most mysterious infinite discrete groups that exist. And it was introduced in around the 65 in the PhD thesis of Thompson. In published notes actually during this PhD. And there are many open questions about it. Many people look at this group, but nobody understands it very well, even 60 years later. Okay, so it's a whole topic in group theory. There are conferences that are called about the Richard Thompson's group. Okay, it's very famous because that's actually the first example of an infinite group that is finitely presented and simple. Okay. Today, we have a classification of every finite simple groups. but we had to wait 65 to have the first example for infinite one. Okay. And today I would say that 90% of every infinite simple groups that exist in the literature, they come from this one. Right? They are tweaked in a certain manner. They are very tweaked. Sometimes it looks like far away, but in every families is there. Okay. The only example that I know that are not like that, they come from Capras and Remy, where they look at some. They look at Moody groups. And maybe the example in Moses that is about a subgroup of automorphism of trees, but yeah. Okay, so it's a very important group. And so when you have a group and you want to understand it, really going, okay, probably digressing a bit too much. When you have a mathematical object like a group or an algebra, and you want to know its property, what do? You go to the blackboard and you look at your object, so like Thomson group T, or maybe after we're going to see the Cuntz algebra, and you ask him, talk to me, tell me something. That's usually what I do. Well, how can I initiate a language with T or O2? Well, there is one way. I need to look at representation of them. Representation of them make me understand them. Make me understanding them. I've quit Australia a year ago. I can't speak English anymore. Harder. Okay, so what the upshot was of the attempt of Vaughan to get like some conformal field theory with beautiful with exotic symmetries never seen before, well, was to find an efficient machine to build representation of this beast. If you come from operator algebra, you would probably say, what are the nicest actions of a group? Well, I would say it has to be linear and it has to be unitary. Okay, I can give you some. So that's great. And for a sister algebra, well, just the classical one star unital representation. Okay, so I could continue to only talk about the Thomson's group. I'm going to talk about the Cuntz algebra. Okay, because the technology works extremely well for it, and the topic of the conference is operator algebra. So maybe let's go more into one specific operator algebra. So what is my goal? Is to grasp some information on representation theory of O2 using the accident of Jones. Okay, the mathematical accident. Okay, we're going to see that in a minute. Okay, so for me, O2 is the so-called Cuntz algebra. So Cuntz did a lot for this algebra, but it is true that it was discovered in 64 by Dixmuir. It was extensively studied in 77 by Cuntz, and Cuntz cites the paper of Dixmuir. But Cuntz did so much that today we usually call it the Cuntz algebra. Okay, and I think it's fair. So what is this algebra? So it's a universal C-star algebra. There is two generators. And what do they satisfy? Well, they satisfy the SI are isometries. Okay, so that's, you write it like that. And then when I look at the adjoints, the direct sum of them is also an isometry. So if you want, yeah, maybe one way to do it, that if I write it like that, this is also an isometry. Okay. And you take a universal algebra, C-star algebra over this condition. And so this is also a very peculiar object in mathematics. Well, that was the first example of, again, something simple. So it's a building block of the theory. It's properly infinite, it's nuclear. Dixmay was looking at that, and he says there must be a quotient of this guy that has all the properties I've never seen before. And Cuntz said, well, actually, you don't need to take a quotient, Jacques. Well, he didn't say that, but I don't know, actually. But it's fine already like that, okay? It is already simple. And it's algebra. I don't say I need to promote this algebra. I'm probably not the best person to say how much it's useful, but it's very useful, for instance, in the classification of simple nuclear sister algebra. Okay, it has like very universal properties. It's been used in a number of contexts. Actually, even been used by Masaki for constructing some nice category, some near group categories, for instance. Okay. And now let's say that I would like to look at the representation category of this guy. So now, again, I'm going to talk to the first person in dealing with sister algebras. I will think, well, I'd like to know a bit more about the irreducible classes of O2, like the spectrum of this sister algebra. Immediately, this person will tell me, don't do that. It's absolutely impossible. Oh, why is that? Well, he told me maybe you're too young to know that, but in the 60s, there is a very important theorem of Glim. What did he say, Glim? He told us that if you find a representation of your sister algebra that is not type 1, you take the bicommutant, and it's not only a direct sum of some B of H, you're in big trouble. Like your spectrum is going to be awful. Okay, so spec O. So for me, spectrum O is irreducible reps of O2, and I caution by saying that one representation is the same than that, where U is a unitary. Okay. So Lim tell me that this is bad because what? Well, because O2 is a non-type 1 sister algebra. Okay. Okay, so in fact, there's a bad topology on the space of irreducible. Like if you take like the primitive ideal, like the kernel, and you take the map that goes there, it's really not, I mean, it will not give you a good topology. So say, okay, oh, that's bad. So I will have a space that will be very, very big by Glim. And moreover, the topology I will have on it will not be Hausdorff, not going to be very good. It's not Hausdorff. Okay, but how bad is it? Well, actually, then you just read what Cuntz. He said, well, it's simple. So auto simple implies that actually the topology on spec, the usual topology on the spectrum is the coarse one. That's true. So the general theory gives you like a natural topology on the spectrum, which is like the inverse image of what you get from the primitive ideal. But since there is no ideal, there is nothing. Okay. So I have a big space and I have no topology. And I claim I still want to find some order in chaos. And why is that? Because I was too naive. I was coming from a different point of view, and now I will explain this point of view. And this point of view, I'm gonna call it Jones technology. It's my last homage to Vaughan. How does it work? It's a wonderful machine. What is it? I'm going to consider something else. I'm interested in isometries. I'm going to take H, a Hilbert space that is complex, and I'm going to consider a map like that. Maybe I call it R. That is an isometry. Okay. So what does that mean? Well, if I take the leg of R, maybe I can call them A and B. It gives me something like that. And then isometric means that is the identity of H. And I look at that, and then if I take the machine of Jones, actually, just with this input, I have a representation of the Thompson's group. Okay. And that was like the original purpose of this work with one was to look at what kind of representation we obtain. Okay. So it was a joint project we started in Maui, I think 2017, I guess. And a bit after Maui, but Jones already had like the beginning, and he very kindly invited me to work on this. Okay. As he was very generous, as we know, with many things. And actually, I think he had a bit pity of me because I got like an accident. And well, anyway, I have like a spare muscle from kite surfing, and he thought it would be nice with me, or maybe I give a subject to Arno, he'll be more happy. Well, anyway. In fact, that made me a bit happy. Yeah. So, okay, so we got that. And any of this input give me a representation of this mysterious Thompson's group that nobody can grasp maybe at all. But there's something else that can happen. Is that now I'm going to take one of these things, one isometry, and I'm going to build a new representation. I'm going to build the representation of the Cuntz algebra. Just for the record, I'm just going to give a name to the sister algebra that is generated by this kind of thing. So it's just the universal sister algebra, two generators, and I just write this condition, and I call it the Pythagorean algebra. Okay, just a name. And so now I want to do a process. I want to promote. I want to promote these two operators. So which is, what is that? Well, it's called the representation of my universal algebra. And I'd like to build a representation of O2. Now, how do I do that? Actually, it's super simple. I'm gonna take trees. Okay. Maybe like this one. So trees such that there is a root here, there's some leaves, and the only thing I'm allowed to write down is a bifurcation, and I can top of a leaf. And then on top of this guy, I'm gonna decorate the leaves, where this psi, they come from my Hilbert space H. Okay, so I look at the collection of all decorated trees, and I put an equivalence relation such that I will have more structure. I will be able to compare guys there. So let's say I want to grow my tree. Grow the trees, they grow in general. If they are healthy. So this one will grow. Maybe I will add a carrot here. One bifurcation. All right, so I keep the same labeling to the other leaves. And now I will change the labeling. I have two more leaves one leaf became two leaves. So what can I do? Well, I'm going to use my A and B. That's the only thing I could do. Oh, A psi 2, B psi 2. Okay, I'm going to say these two guys are the same. Right. And I take the collection of all these label tree and the classes of them with respect to the equivalence relation related by that. Okay, so that gives me a new Hilbert space that I will call pi of H. And here I have natural operation that I can look. So now that I can draw, it's super easy to maybe to define some operator. So let's say that let's take the same guy actually. Like one operation could be, I only care to what is here. Okay, I forget the right-hand side. Okay, so I do that. Actually, I don't like that. No, I'm gonna add a caret below. So I'm gonna do that, and here I will reproduce my tree. Okay, so what is new is this part. And here I have one more leaf. I say, well, okay, I put 0. I could do that on the left, but I can also do that on the right. So I have my new guys here. Here I put 0 and I reproduce my my vector. Okay. Give me some maps. I can check if it's coherent with my equivalence relation. There's no problem. I'm going to call that S0. I'm going to call that S1. Surprise, it's a representation of the Cuntz algebra. Ah, great. So actually, this new things is a representation of O2. So now what are the nice things here that's going on? So a few facts. Pi is actually a functor. Okay, it's always nice to have. Now, actually, since I built the new representation, it's a representation of the Cuntz algebra, but as you may see from the presentation of my 2 algebra, Cuntz is actually a quotient of my Pythagorean one. So I could actually take this representation that is bigger of the Cuntz and reapply my process. What will happen? Nothing. It would be equivalent. But what does that tell me? It tells me that here, I'm essentially surjective. It means that every representation of the Cuntz algebra can be written in that way. So it's almost tautologic to prove, yeah. It's nothing is there's almost nothing to do. But the second thing is that so for any representation, let's say, how should I write it here? A kappa, the representation of the Cuntz algebra. There exists a representation of my little algebra P such that when I apply my functor to my first representation, I get the other one. Great. So every representation of the Cuntz algebra are like that. So perhaps now with this point of view, I will be able to do something about the spectrum. I will be able to say something. And indeed, that's what will happen. Okay, so let's erase and let's explain something nice that happens here. Okay, so I started at quarter past.
Yeah, so you have still 15 minutes.
I know I talk too much and okay. Maybe we'll not see the tensor product.
Now you have to talk twice as fast.
Oh, yeah, do that, yeah, exactly.
Very easy.
Just gonna talk super quickly. Good plan. Okay, so what do we get? Okay, so perhaps now I'm gonna say, where is the miracle? John always says there's a miracle somewhere. So here there's actually a miracle, which is true. The miracle was something I didn't think was true. And Dilshan, my student, convinced me it was true. Yeah. So maybe I call it Dilshan miracle. Because we had like a ad hoc proof for a very specific case that was like filling many boards that's super technical and ugly. And now there is like a half-page argument that is super general. So, well. Mathematics, huh? Okay. So now I take, let's say, H, a representation of my Pythagorean. So that is only defined by one isometry from H to H plus H. And E is something like that. That is isometric. And the map is given by A plus B. Well, this I know will give me a representation of the Cuntz algebra if I apply my functor. And you could say that there's many of such choice of A plus B that can give me the same representation. But actually, you need to do a representation theory that is more subtle on H, meaning you want to decompose with respect to the algebra generated by AB rather than, how to say, the star algebra generated by AB. It's extremely weird to do that when you work in operator algebra. You will say, now we'll forget about the adjoint. I just want to look at Hilbert subspace that are closed under A and B, but maybe not from the adjoint. Okay. If I do that, I've never seen that. Maybe Corey, who knows all the decomposition, all the things. I don't know if you've seen that before. There'll be a unique way to write down. So let's say now dim H is finite. There'll be a unique way to write this guy like that, Hn, plus something. So something I could call it G for garbage is a vector subspace that do not contain anything closed under A and B. Very strange, huh? So it's not semi-simple, but almost. And now I apply my functor. And this functor will give me, well, for each of these guys, I have something. The Z is forgotten. And moreover, this guy, they are irreducible as reps of the Cuntz algebra. And this decomposition is unique. So what does that mean? It means that if I'm clever enough, I can fully work on this sister algebra. It is much more manageable and get result on the Cuntz algebra. Okay, and now let me give you some good structure on this spectrum that was told to be very bad. Yeah, right. Now what I'm going to do is that I'm going to look at the irreducible for the manageable sister algebra that do not have this bad space, this garbage space. And I can see that if I fix the dimension D, okay, it's not infinite. Well, the irrep of P such that this space is trivial, okay? So that's the right irreducible, like they are very irreducible if you want. And I mod out. Well, this will give me actually a structure of a smooth manifold. A smooth manifold of dimension, or real dimension, 2D squared plus 1. Okay. So what does that mean? Then now I come back to my spectrum. I come back to my spectrum of O2. And now I can say that this dimension D actually is going to be an invariant for the representation upstairs, for the Cuntz algebra. I can decompose into some pieces. And this guy, if D is not the infinite, this is in bijection with a smooth manifold of dimension 2D squared plus 1. Okay. So finally, I could say that actually all this warning about not looking at the spectrum of Cuntz algebra, you know, they were, it was a good thing that I didn't listen to them. Yeah. Because with this Jones technology, I could really bypass them because it was a new idea. And we've pushed the chaos, all the chaos now that was given by Glimpse theorem is contained in the guys that are infinite, but very infinite in a certain manner. Okay. I should recall that every representation of the Cuntz algebra are necessarily of infinite dimension. So here I have a new dimension function for the representation of the Cuntz algebra, but that's, I know it because I can use the Pythagorean algebra.
Does this topology on these smooth manifolds play nicely with the Fell topology for the representations, like convergence of states, or is it like totally disjoint from usual?
I need to think about it. Yeah, it's something I haven't looked, but it's a very natural question. You're right. Yeah, yeah. Will be interesting to see. Yeah, here it's really more like we get like really a smooth manifold there. Maybe I should say what is the first one. So the first one is special because it corresponds to isometries from C to C plus C. Okay, complex number, and you do that. And because it's dimension 1 and we deal with numbers and everything commutes, they're going to be pairwise non-isomorphic immediately for the Pythagorean algebra. And then with my machine, it will work. With the machine with Jones, it will work. Okay. And this, if I write that, that's the isometric condition. So I exactly get the real three sphere. Complex numbers such that. If I take dimension 2, I have to deal with 2 by 2 matrices. It's more complicated. I need to mod out. Basically, in them 2, I will have the same thing like isometrics, but I will get like a manifold. And I will mod out by the action of PSU2. Okay. So actually, I get a manifold of dimension 3 times 2 square. Then I will reduce the dimension with this group. Okay. Because I will take the orbit space that will give me again a manifold structure because the action is nice. All right. So I'm happy. I got like some geometric invariant, some geometric description of the spectrum of my Cuntz algebra. But actually, I could go even further. So I'm not going to explain in details. But I can also put like a tensor product. And how do I do that? Well, in few words. So I have a way to go from rep P to rep O. I have my Pythagorean functor, this pi that we've seen. And if I limit well, actually, I could locate inside all the guys that don't have the garbage subspace. Okay. And when I do that, it's going to become fully faithful. Now I can come back. How do I do? The comeback is inside of the representation of the Cuntz algebra, I can locate this decomposition. It's still inside, and there is a way to find it inside. Well, this I didn't explain at all, but let's say it's on the image of that, I can come back. I get an equivalence of categories. And so now all I need to do is to make a tensor product here and to push it. How can I do that? Well, now
it is not simply that, okay, you look at a representation of O like a representation of T, it's kernel.
No, it's not. It's
Not that.
but there's one step is like that. So you take a representation of O. You can thinking with these trees. Okay. And then inside that, you're going to see what is closed under the action of this guy. So the adjoint of Cuntz, they correspond to A and B. And you look at the smallest subspace closed under this guy that will generate everything as a representation of the Cuntz algebra. And if you start with something finite dimensional, this will exist. There will be a smallest one. In general, it does not. And the smallest one will be exactly this thing. So actually, everything that has a non-trivial tree will be in Z here. You will reduce to stuff that are like that here. Okay, with a trivial tree. And that will give you your sigma. It will give you the smallest subspace such that blah, blah, blah. Okay. And if you look at P, this is really like you only need to deal with two isometries, like A and B, such that they give you an isometries. And in some sense, it's taking the Cuntz algebra, removing some relation. Here, roughly, you could think that this is like the free algebra. Almost. So if I will have two pairs, like that, I would just take the tensor product. But I need to rescale. I will rescale with an operator, and my operator will be the only thing you could take. It's going to be the square root of something like that. And then I add my b's. So I take the tensor product, the usual one. We are not in the free world of pure algebras. We have some isometric conditions, so I need to rescale. And that does the job. And I can compute. And I get some rigid C-star tensor category. Okay, all the axioms are fulfilled except that we have uncountably many objects. Okay, but everything works. Now, just in 1 minute, this is a beautiful story, but I could do everything completely algebraically. Okay, instead of taking the Cuntz algebra, I will take the Leavitt algebra. And my Pythagorean algebra will be literally replaced by the free algebra. And so on the free algebra, I can do a tensor product, everything works. I can do the same discourse about moduli space. But now, instead of having like smooth manifold, I will get some smooth algebraic variety. And instead of acting with like some ESU, I will act with some PGLN. Everything works the same. The techniques are different. Here we could use semi-simplicity in a certain manner, I mean, almost. In algebra, there is no semi-simplicity, but there are other tricks we can use. So it's two different proofs with similar scheme. Okay. And so this is one example of what can we do with this kind of idea that came from this dream of Vaughan of conformal field theory. Here I did it for binary with the second Cuntz algebra. It can be done with for any Cuntz algebra, finite. At some maybe one can look at Kuntz-Krüger algebra. Okay, so there are a lot of candidates where this could be applied for algebra, for C-star algebra, and also for group. Okay. So we started from subfactor theory and conformal field theory, and we arrive in computation theory of C-star algebra and other objects. So I guess I should stop. So thank you for your attention.